I will talk about, it's about ISS, right? So I think we can safely skip table of contents and directly go to the first slide, where I just want to remind you of some work that has been done on a small gain approach for input to state stability of finite networks. So this is an approach that you can find, or that was developed in a number of papers around 2010. The most prominent of these papers and the most cited you can see here in the footnote. And this approach, well, works as follows, or the setup here is as follows. You have finite number of control systems like that here, each one described by a nonlinear ODE. So we have n of those subsystems. And this approach actually provides a method to construct an ISS-Lyapunov function for the overall system that you get by putting all these subsystems together from ISS-Lyapunov functions of the subsystems. And central to this approach is a monotone operator gamma, which is called gain operator, and which acts on this cone Rn plus, which is basically the positive orthant in the Euclidean space Rn. Then in terms of this operator, you can write a small gain condition actually in three, or at least three equivalent ways. One of these ways is in terms of a path which evolves in the decay set of this operator. The second is in terms of the asymptotic stability of the discrete time system, which is generated by iterating the operator. And the third one is in terms of the behavior of the operator in one time step. So this third one, it's also known as the node joint increase condition. I will tell you exactly what that is later in my talk. So this was just to remind you a little bit of what my talk here actually is based on, or what I'm actually talking about, because my aim is to generalize this approach for finite networks to infinite networks. Not to all kinds of infinite networks, but to certain class of infinite networks, which I'm now going to define on the next slide. So we need a certain convenient setup for these infinite networks. Again, we have subsystems or individual systems, which I call sigma I. Again, each of them is described by an ODE, very similar to the last slide. Here, the xi's are the state vectors. I'm assuming that everything here is finite dimensional. So xi lives in some finite dimensional Euclidean space. The dimensions, they can vary. They don't have to be the same for all the subsystems. Then we have an xi bar, which is also finite dimensional. And it's actually a tuple of state vectors of neighboring subsystems, xj, where the index j ranges through some finite set of neighboring indices. So that's an important assumption here. I'm assuming that each of these subsystems can only be influenced by finitely many other subsystems. And of course, we have the external input, control input, or however you want to interpret this, ui, which is also finite dimensional. And we are basically only assuming that unique solutions to initial value problems for an appropriate class of internal and external inputs exist for all of these subsystems. Then again, we can put all of these subsystems together to form the overall system, or the network, or the interconnection of these subsystems. So basically, we just put all these right-hand sides together to form one infinite vector like that, where the xi's are now the components of some infinite vector x, and the same for the ui's. And we want to do this in such a way that we can write at least formally, we can write this as, well, we can write the overall system as an ODE, a well-defined ODE in some Banner space. So we need to define this space and some other spaces too to make sense of this ODE. So first, the state space. So the state space is the space where X lives, of course. So an X now is the vector of all the Xi's, all the states of the subsystems. And I'm assuming here only that the supremum over the norms of those Xi's is finite. When I say norm, of course, I have not defined a norm. You have a lot of norms on any Euclidean space. The idea here is that you can fix a norm on each of these spaces, R and I, and you can do this as you wish. But you need to fix it, and then you can make all the definitions. So this is a state space. Then we do the same thing for the control space. And we also need a space of control inputs or control functions. So this will be capital L infinity space. So basically, this is essentially bounded functions into the control space, right? And all of these spaces are equipped with supremum norms. So in this sense, they become Banner spaces. And under certain conditions that I don't want to write down, it's just like usual conditions like Lipschitz continuity in X and something like that, you can show that for this ODE, you have a unique solution once you fix the initial value and you fix the external input u. So, and we denote these solutions by phi of txu as usual. If you have questions about this, of course, you can ask at any time, right? So this is my setup for the infinite networks. And of course, we can define input to state stability for this overall system or for the interconnection. This is just the usual definition. I think I don't have to say very much about this. The only thing is that the norms that I'm using here, this X norm and this calligraphic U norm, these are the norms from the Banner spaces that I just defined. So this is the supremum norm and this is the L infinity norm. Then we also have a notion of an ISS-Lyapunov function. Here I'm defining this in an implication form. I could also do it in dissipation form, but I decided here to use the implication form. So this is just, so what is an ISS-Lyapunov function? It's a continuous function from the state space to R plus, which is coercive, which means that we have K infinity functions, which give us bounds like this here. And we have an implication like this. I think this should be well known. The only thing here maybe I should mention is the kind of derivative that I'm using here, or orbital derivative. This is basically the right upper Dini orbital derivative that you define using a limit superior. So this is this, and then we have a well-known fact. If an ISS-Lyapunov function like that exists, then the system is ISS. I'm not sure if the converse here holds. I think nothing like that has been proven. I don't know, Andrei, maybe you can say something about this.
Well, there was a result by Fabian-Wirth and me in systems control letters, which shows that if the nonlinearity f, which you have constructed from all these right-hand sides, if it is Lipschitz continuous in X and U, then we have the converse result. But it should be Lipschitz continuous in U as well.
Nice. Okay, thank you. I was not aware of that. Okay, so but here I don't need the converse. I just need this. So the idea is now we want to if we want to prove that the network is ISS, we can do it by construction of a Lyapunov function, right? And there is a small gain approach to this that has been developed already in the paper that you can see here in the footnote from 2022, together with Andrei and Mashid Zamani. And this small gain approach shows that under certain assumptions, an ISS-Lyapunov function V for the overall system can be constructed from ISS-Lyapunov functions Vi for all the subsystems in a way as you can see here. So V of x, well, you take the components of this vector x, the xi's, you apply the Lyapunov functions of the subsystems, and you also apply some scaling. This is an inverse of a function sigma I, and then you take the supremum over all of this. So what is the sigma I? The sigma i's are the components of a certain path, sigma from R plus into L infinity plus. Well, what is this? Well, what the properties of these paths I will define a few slides later, but what is L infinity plus? This is, again, a cone in some Banach space. For finite networks, it was like the positive cone in the Euclidean space. And here it's something similar. Here we have, as the overall vector space, we have small L infinity, which is the space of all bounded sequences of real numbers. And L infinity plus consists of those sequences which have non-negative components, right? So this is a cone. And together with this cone, we have an ordered Banach space, which is this pair here. So let me introduce some concepts and some definitions for this ordered Banach space that I will in the following use. Unfortunately, there are a lot of technical definitions in this talk, but I don't see a way how to do it without giving all these definitions anyway. So what are the concepts that we need? Well, first, it's easy to see that the cone is closed in L infinity and it has non-empty interior. Then, as usual, the cone induces a partial order on the vector space in the usual way, as you can see here. Then we also have a notation for two vectors, S1 and S2, that one is strictly less than the other if the difference is in the interior of the cone. So this is also a usual notation actually for ordered Banach spaces. Then one other thing that I'm going to use a lot of times is this particular vector 1, whose components are all ones. So you could also say this is the sum of all the unit vectors in L infinity. Then another important operation that we need is it's a binary operation on L infinity plus, and it's a component-wise max operation. So if we have two vectors, S1 and S2, then this thing here is defined as the vector whose components are the maxima of the corresponding components of the two vectors. So first, this is a binary operation, but then, of course, you can extend it to arbitrary families of vectors by replacing the maximum with the supremum. So next thing is, if I fix a subset I of my index set, n, the natural numbers, then I define some space, some subspace of L infinity plus. It's L infinity plus of I. It's only those components which are non-zero whenever the index, or can be non-zero only when the index small I is in this subset capital I. So for all indices which are outside capital I, it's 0. And finally, if we take any vector S, we can define a projection to this subset, which just means that we are only considering those components as I with I in capital I, and the rest we forget about them. So we just project S to this subspace. Right, so these are some necessary definitions. Now let's come back to the small gain approach. So I said we construct an ISS-Lyapunov function for the overall system from the Lyapunov functions of the subsystems, Vi. So what does it mean that Vi is an ISS-Lyapunov function of sigma I of the subsystem? It basically means that we have an inequality like this, which is very similar to the one that I had for the overall system, for the overall Lyapunov function. There are some differences here, where the most important one is that this ISS for the subsystem means ISS with respect to external and internal inputs. So here you see a term which relates to the external input, but you also have a term which relates to the internal inputs. And this is a bit complicated because it involves a couple of functions. It involves the ISS Lyapunov functions of the neighboring systems, the Vj. It involves some gamma ij's, which I just call gains or interconnection gains, and some function mu I, which I call a monotone aggregation function. So let me see, and some other functions are involved here, but this is basically usual things that I think I don't have to say much about that. The important thing here is what are these gamma ij's and what are the mu i's? The gamma ij's, the interconnection gains, are basically k-infinity functions if that second index j is in the set of neighboring indices of the system I. So it's in this set, and otherwise it's 0. So this relates to the assumption that the subsystem with the index I is only influenced by subsystems with the indices j in this set capital I, index small I, this finite set. So, right, so these are the interconnection gains, and then we also have the mu i's, which we call monotone aggregation functions. This I will define precisely what that is on the next slide, but here I only give 2 examples. It could be, for instance, a sum, or it also could be a supremum, but it can be a lot more things actually, right? So by letting this mu I vary through a lot of possible different functions, I'm allowing here a lot of possible different formulations of the ISS Lyapunov function property or this implication. So a lot of different formulations of ISS, like a sum type formulation or a subtype formulations, and also a lot of others. So that's basically the idea here. Right. So monotone aggregation functions. So actually, what do I assume about them? So these monotone aggregation functions, mu I in general, they are functions from the cone into the closed interval 0 infinity. So they can take the value infinity actually, and they should satisfy a bunch of properties. First one is uniform positive definiteness. This means they're mapping 0 to 0, and there exists a k-infinity function psi such that we can bound them from below by psi of the norm of the vector s for all I and for all s. So this means uniformly in the index and over the whole cone. Then we have monotonicity. Monotonicity basically says if we have 2 vectors S1 and S2, which are related by our partial order, then if we evaluate the mu I at these vectors, we get the same type of inequality. Third property I call finite continuity. That means if I take a finite subset of my index set, capital I, and I restrict the function mu I to the space L infinity plus of I that I defined before, then this restriction is finite valued and continuous. So for instance, if I go back here, if you think of the sum, if I restrict this sum to vectors which only have finitely many components non-zero, then of course that's a continuous function and it's finite valued. But if I allow sums over all the components, then this can take infinite values. This can become infinite. So I have to make this restriction to say something about continuity. And this is this here. And I have a fourth property, which I call local equicontinuity, where I don't want to go like exactly through these definitions. On the next slide, I will show you actually why I need the assumption. Basically, it's an equicontinuity assumption about all the mu i's, which should hold on bounded subsets of the cone. So let me first, now we are at the point where I can define actually the gain operators. So this is really nice. Now we have everything put together to give a definition of the gain operator. The gain operator gamma, that's an operator on the cone. So it goes from L infinity plus to L infinity plus. And it's always a gain operator associated with fixed interconnection gains, gamma ij, and fixed monotone aggregation functions, mu I. And it's defined in this way. So of course, it has component functions, gamma I of s, and gamma I of s is defined in the way you can see here, via those interconnection gains and also the monotone aggregation function. And now you can already see a connection to the definition of the ISS-Lyapunov property for the subsystems, because here you see basically the gain operator or the component I of the gain operator popping up here. So you can easily see that you can write this now in terms of the gain operator. So this is where the definition comes from, right? So this is how I define the gain operators. It has some nice properties which directly follow from the properties that I put here. First, it's well-defined. So its values are always in the cone. Then it maps 0 to 0, and it's a monotone operator. Monotone operator means you have this implication here. It's continuous in the norm topology, which is important. This basically directly follows, I think it's even equivalent to this local equicontinuity property. And the fourth property, which is even more important because I'm using it more often, it's that gamma is also sequentially continuous in the weak star topology of the Banach space L infinity. Just to remind you, L infinity is the dual space of L1, and in every dual space we have a weak star topology, and we can talk about continuity in this topology. This property of sequential continuity in the weak star topology is a direct consequence of the finite continuity here. So this is the reason why I need the finite continuity. One of the reasons. So what does it actually mean? Sequentially continuous in the weak star topology. We can put this in a way which is a lot better, or it's better understandable. So we know what it actually means. It means that whenever we have a sequence Sn in the cone, which is norm bounded and which converges in every component to some limit vector S, so it's component-wise convergent, then the image of that sequence under the gain operator is again norm-bounded, and then again it converges component-wise to the image of that vector S. So that's what it means. And in particular, this implies that if the sequence here happens to be a trajectory of the gain operator, so if Sn is like the nth iteration of gamma applied to some fixed vector S0, then from that we easily see that the limit vector S must be a fixed point of gamma, right? So this I will use actually, or I'm using a lot of times. So this is the gain operator. I will need some related definitions to that. Maybe the most important one is the decay set. The decay set of the operator is a set psi of gamma, which consists of all vectors such that gamma of S is less than or equal to S, in terms, of course, of this partial order defined by the cone. Then next thing, if we take any k-infinity function phi, it acts as a monotone operator on the cone. by simply applying phi. If we apply phi to some vector s, we simply apply this k-infinity function to each component of the vector. So this gives a monotone continuous operator, actually. And we are using this type of operator to define a scaled gain operator. For any k-infinity function rho, we define the scaled gain operator gamma rho, which is the following. It's taking the identity function on R plus this k-infinity function. So this sum will again be a k-infinity function. And I interpret this as an operator like defined here. So then I can compose it with the gain operator. So this is the composition of two monotone operators. So again, it's a monotone operator. And actually, one can show that this is again a gain operator, which has the same interconnection gains, but scaled monotone aggregation functions, just like that, right? So if we take a function rho, which is has quite small values, then this is like you can think of this as a slightly enlarged gain operator, actually, because it's making the components, all the components, a little bit larger. All right, next definition. A subset A of the cone will be called cofinal if for every S in the cone, there is some S hat in the set A, such that at S hat is bigger than or equal to S. This is a usual notion of cofinality. And I also need a notion of uniform cofinality, which means that I have the same property, but additionally, I can always choose the S hat such that its norm is bounded by some k-infinity function phi of the norm of S. And of course, this k-infinity function phi needs to be the same for all S. So basically, it says that there exists some phi such that this holds for every S, right? And finally, we will talk about the discrete time systems, which are generated by iterating those operators, gamma and gamma rho. And we denote them by sigma and sigma rho, respectively. So sigma from now on will no longer be like our notation or our symbol for this overall system, which is the Banner space ODE, but from now on, actually, it will denote the discrete time system generated by the gain operator. Right. Next thing I need are some stability notions for monotone systems. Unfortunately, as I said, a lot of definitions. So given any monotone operator T, which acts on this cone, which maps 0 to 0, so it has 0 as an equilibrium point, we consider the discrete time system generated by T, which is this one. And we call it uniformly globally stable, or UGS. It's just the usual definition. If there exists a k-infinity function phi such that we have this here for the iterates of T. And the next thing is also the usual definition, uniform global asymptotic stability, or UGAS. If there exists a beta, a KL function with this property, then we have global attractivity, or GAT, which just means that every trajectory goes to 0 with respect to the Banner space norm. And we have a weaker notion, which is weakly star global attractivity, or GAT star. Means the same thing, but with respect to the weak star topology. So for every S, the trajectory should converge to 0 in the weak star topology, which means, just to remind you, that the sequence of iterates, or this trajectory, it's norm bounded, and it converges to 0 component-wise. Then it's pretty clear that UGAS implies global attractivity, and this implies the weak star version of global attractivity, and also UGAS implies uniform global stability. But we can show here a little bit more, actually, from the monotonicity of the operator and the result of André that you can find in the paper in the footnote. We can conclude that UGAS in this particular case is equivalent to uniform global stability and global attractivity. Though those two together are enough to give UGAs. So that's just, I'm using this as a fact here. So now I can finally come to the definition of a path of decay or strict decay, which will turn out to be our small gain condition. I'm giving you a definition here actually, which is already simplified. There is a theorem behind it. If you look into the paper that maybe I can go back. If you look into, not this paper, but this paper here, where I said you find the small gain approach here. If you look into this paper and you look for the definition of a path of strict decay, you will define a slightly different definition, which is more complicated than that one, but it can actually be simplified, and that's the simplified version. So a path sigma evolving in the cone, we call a path of strict decay if it has those four properties. The first one is strict decay, which means that the values of the path are all in the decay set of the enlarged gain operator gamma rho for some rho, right? So this is a strict decay condition. Next one is a coercivity condition, that we have k infinity functions, phi underline, phi overline, with inequalities like this here for all r. Then we need monotonicity, which we can also say that sigma is increasing. So if R1 less than or equal R2, then the same inequality holds for the values. And finally, continuity. We want sigma to be continuous in a norm topology. So if all of these properties holds, we call the path a path of strict decay for the given gain operator, of course. And if all of this holds, but with only one difference, that instead of a k infinity function here, we have rho identically equal to 0, which means that gamma rho becomes gamma, then we call it a path of decay. So there is no strict decay here. Now there's only a decay. With this enlarged gain operator, we have strict decay. And the fact here is the important fact, or the crucial fact, is that the existence of such a path of strict decay is actually the small gain condition. So if such a path exists, then the overall Lyapunov function can be constructed from the individual Lyapunov functions. So I could actually stop here and say that's a small gain condition. We have a small gain theorem. But of course, this definition, well, how do you find such a path? That's a big question. How can you know that such a path exists? You have to come up with some definition of that path, and you have to verify all of these properties. So actually what we're aiming at characterizations of the existence of such a path, which can be verified, at least in certain examples or certain classes of gain operators. So this is, like the rest of the talk, is dedicated to finding conditions for the existence of such a path, which are somewhat easier to understand or to apply, right? Are there any questions until here? If not, let me continue. So the first thing that I'm doing here to say something about the existence of a path of strict decay, I define some associated operators associated with a given gain operator. First one is the one that I call augmented gain operator, so gamma hat of S. So what is this? This is the component-wise maximum of S and gamma of S. Again, this will be a monotone operator, not hard to see. Then another type of operator, actually a family of operators. For every B in the cone, we define an operator like this. So instead of S here, I'm putting a fixed vector B. So this will be called gamma B, and again, it's a monotone operator. So why am I introducing these operators? What are their properties? Well, first, so this is these are properties which are like the same as for gamma. They share these properties. They are both monotone operators, they are continuous, and they are sequentially continuous in the weak star topology. So this is easy to show. Then a property of this augmented gain operators, the trajectories of these operators are of this operator are increasing. So this is easy to see because we are always taking here the maximum component-wise with the vector S. We will never get a vector if we apply gamma hat. We'll never get a vector which will be in any component less than S because we're taking the maximum with S. And then using monotonicity, it follows that actually the whole trajectory is component-wise increasing, which is what I wrote here. Then next property, if we look at the fixed points of this augmented gain operator, so what does it mean for S to be a fixed point of this? If this thing here is equal to S, then it means that this component-wise maximum is always achieved at some component of the component of S and not of gamma of S. So that means gamma I of S will never be larger than Si. So what that's just saying that S is a point of decay for gamma. So the fixed point set of gamma hat is exactly the set of decay of gamma. And well, what can we say about the other operator? If we have a point of decay for this operator, then it's also a point of decay for gamma. Because, well, saying that this is a point of decay for this, that's even stricter than saying that it's a point of decay for gamma, because we have the maximum with B here. So we have this inclusion. And then fourth property, which is not quite trivial, but it can be proved by induction. If we iterate this augmented gain operator on some vector S, then it's the same as if we iterate the gamma S operator. So putting B equal to S and apply this to S. So this holds true for all S and for all N, and it's proved by induction and using monotonicity only of these operators. Right. And again, we need a notation for the discrete time systems, which are generated by the operators. So this is just sigma hat and sigma B, respectively. Right, now we can prove our first result, which will show you why well, at least some of the definitions, why I introduced these operators, or this augmented gain operator at least. So this is an equivalence of 4 properties. The first one says the system sigma hat is uniformly globally stable. It's equivalent to the existence of a path sigma in the cone, which already satisfies the first 3 properties of a path of decay. So it's not quite a path of decay. The only thing that's missing here actually from the properties is the 4th one, which was continuity. But all the other properties hold: strict decay, coercivity, and monotonicity. So this is equivalent, which is already nice. It's also equivalent to the existence of a path sigma, which satisfies only the first 2 properties. And it's equivalent to this decay set of gamma being uniformly cofinal. Right. To prove this, actually, most of the implications are quite simple. The only one for which you need an idea is how do you get from A to B? So how do you actually come up with that path? And you can do it in the following way. You can define this path sigma by sigma of R, putting equal to the component-wise supremum over the whole trajectory or some trajectory of this augmented gain operator. And what is the initial value of this trajectory? It's R times this 1 vector. So that's the vector whose components are all equal to R, where R is the argument here. So that's a non-negative real number. And as I told you, the trajectories are increasing. So what does it mean to take a component-wise supremum? It's actually the same as saying taking the component-wise limit. because if it's increasing, then the limit will be the supremum. So this is actually the same as saying that sigma of r is the weak star limit of this sequence, which is the trajectory that you see here. And then we can use weak star sequential continuity of the gamma hat operator, which directly shows that sigma of r must be a fixed point of gamma hat. But the fixed point of gamma hat, as I showed on the last slide, is nothing but a point of decay of gamma. So in that way, we show that by this definition, we get a path which actually evolves in the decay set of the gain operator gamma, which is the first property that we need for a path of decay. And the other, well, the second and the third properties are kind of easy to show. Right, so this is how we do that. Keep this definition in mind because it will come up later again. So, right. Let me think a little bit how to get from this slide to the next one. Well, okay, we have not yet a path of strict or a path of decay here because the continuity is missing. And if we look at those properties A or D, well, saying that the system is UGS, it's something, I mean, how do you verify that? So it's not yet really satisfying. So we would like to have a characterization or at least a sufficient condition for the system sigma hat to be UGS. And this is what actually comes next. And it makes a connection to what has been done for finite networks. So this is a property which I call the max MBI property, which you can already find in those papers that I mentioned in the beginning, those papers around 2010 on finite networks. So this is the max MBI property, where MBI stands for monotone bounded invertibility. I will, in a moment, I will tell you why I chose this name. So, but first the definition. I say that gamma satisfies this property if there is a k-infinity function phi, such that we have an implication like that here. So for all b and s in the cone, if s is less than or equal to gamma b of s, it must follow that the norm of s is bounded above by phi of the norm of b. So what does that mean? Probably it looks a bit strange. You might have never seen this before or something similar, but actually you have seen something like this, because if you would replace here this this maximum, this component-wise maximum operation with the usual sum or plus operator, so then you would have here b plus gamma of s, and then if you additionally assume that your operator is a linear operator, linear bounded operator, and you assuming that this function phi is also a linear function, then this is exactly what is called monotone bounded invertibility in functional analysis. So this is why I chose this name. So it's actually related to something that you might know. Right. So why do I introduce this property? It has two important implications. First one, if it holds, then the gamma hat system will be uniformly globally stable, which is very easy to see. Well, first, like since trajectories of gamma hat are increasing, we have this inequality, but using this property here, which is proved by induction, this here is actually the same as this here. And now we compare this inequality to this one here. So if we replace this S by this guy and B by S, then this definition just says that the norm of gamma hat to the n of S must be bounded by phi of the norm of S for some k-infinity function phi, which is independent of everything. So this precisely means that the system is UGS. So we can prove this very easily. Second implication, the system which is generated by the gain operator gamma itself will be globally attractive in the weak star topology. Why is that? For every S in the cone, we can find an S hat, which is a point of decay of gamma and which is bigger than or equal to S. This is because of the first property, actually. Now, if we look at this inequality and you use that gamma is a monotone operator, we will see that if we iterate gamma on this S hat, we get a decreasing trajectory, component-wise decreasing. So if it's component-wise decreasing, in every component, it must converge to something. And it's also norm-bounded. So that means that it weakly star converges to a fixed point of gamma. But as you can easily see from this property, if you put the vector b equal to 0, so what does that mean? If you have a fixed point, if you put b equal to 0, then gamma b equals gamma. So if you have a fixed point of gamma, then you have, in particular, this inequality, but then this tells you that the norm of the fixed point is bounded by phi of 0, but that's 0 for a k-infinity function. So S itself must be 0. So that means gamma can have only one fixed point, which is 0, which is the origin. So this is how you see that the system is God star. So every trajectory must converge weakly star to 0. So we have those two implications from this max MBI property. Right. Actually, I don't have a time here. Andre, how much time is left? Or Patrick?
Well, it's usually 50 minutes, but if you have 10 minutes more,
Sorry?
it's okay. 10 minutes more is good.
No, how much time is left?
10 minutes.
Only 10 minutes. Okay, we won't get that far, but doesn't matter. I can show you some more results. So what about, well, we already have now a necessary condition actually for the existence of a path where you can interpret this as a necessary condition, because if a path exists, then in particular a path with the first three properties exists. So then a necessary condition is that this sigma hat system is UGS. But maybe we have some more necessary conditions. And indeed, we can prove this theorem. If a sigma admits a path of strict decay, then there exists a k-infinity function rho, such that two things hold. First, the system induced by the enlarged gain operator gamma rho will be UGAS. And second property, now comes again the max MBI property, that gamma rho actually will satisfy the max MBI property. So this is something that can be proved. It's not too hard. Well, now one can think, now looking at this theorem, one can think, well, maybe those two properties in A and B are related. Maybe they are actually equivalent, or at least one implies the other. But what we can show is that in general, the max MBI property does not imply UGAS. That can be seen by counterexamples. So this implication certainly does not hold in general. And about the other implication, well, cannot prove anything, but it seems unlikely that UGAS in general implies this max MBI property, because I have a characterization of the max MBI property, which makes it seem unlikely. So my conjecture would be that these are two independent properties that you get from the existence of a path of strict decay, right? Now, let me see, what can I do in the remaining time? Well, what we have not really done until now is really constructing a path of strict decay. So what assumptions do we need? Sufficient conditions to guarantee the existence of a path of strict decay. Well, if you look into the literature, both on finite and on infinite networks, on those two small gain approaches, you basically find two different methods to construct a path. The first one I already showed you. This was this year that I used in that proof before. So this would definitely be a candidate path. If we are assuming that sigma hat is UGS, we can define this, and we already know that it has the first three properties of a path of decay. So maybe it's also continuous under some assumptions, and then we would have a path of decay. And if we apply it to an enlarged gain operator, we would have a path of strict decay. So it only remains to prove continuity to show this. So this is the first method. Second method that you find in the literature about the finite networks. In this case, the path construction can actually be reduced to the irreducible case, which means the case when the interconnection graph that you can define for your network, when that one is strongly connected. In this case, it can be shown that if we assume that the sigma system is UGAS, then one finds always a point S0 in the interior of the positive cone, which admits a complete orbit. So complete orbit means it goes forward and backward in time. So it has pre-images. So this is this orbit Sn. And then if we connect all the points Sn by linear segments, we get a piecewise linear path. And this will actually be a path of decay. So those are the two methods. And I looked at these two methods and checked what kind of sufficient conditions do they give us here in this setup of infinite networks? Well, let's first look at the first method, this candidate path. Here we can show following theorem. First one, the point sigma star of R for any R. So this point is a fixed point of this operator. And it's actually also the minimum of the decay set of this operator. That means it's an element of the decay set. And for any other element S, we have this inequality. So in that sense, it's the minimum. And we can show if the fixed point is actually unique, if there is no other fixed point for this operator, for every R, then already the component functions of sigma star must be continuous. And if we have more, namely that it's not only the unique fixed point, but that it's a globally attractive fixed point for every R, then we can show that the whole sigma star is continuous. That means a path of decay. So here we have like a first sufficient condition for the existence of a path of decay. We need this global attractivity, right? And so under additional assumptions, which are, well, a bit restrictive, but not too much, we can actually show that this condition, the uniqueness of the fixed point, is actually also necessary for the continuity. So we don't get around this if we want this path sigma star to be a path of decay. And one other remark, this assumption C here is actually closely related to a concept which is called static input state characteristic, which was introduced by Angeli and Sontag in the paper that you see in this footnote here. And it was introduced for the analysis of monotone control systems. And the monotone control system to be considered here is the one that I put in parentheses. And now I think my time will run up, right? Andri?
5 minutes you still have, so.
5 minutes?
Yes.
Okay, then I can still say something about the other method, the linear interpolation method. Can it be applied in the case of an infinite network? Well, first, an observation. We had this coercivity condition in the definition of a path of decay. So this was the second condition actually in this definition. Now this implies something, namely this inequality that you can see here. Why is this implied? Because, well, if we first use the first inequality, we see that sigma of R is bounded below by this guy, but then the R, which pops up here, we can use the second inequality to bound this R by sigma overline inverse of sigma of R. So this is just another way of writing the second inequality. And in that way, we see that this inequality here holds for every R. So this observation leads to a definition. So the definition is the following. I call a set A in the cone coercive if there exists some k-infinity function phi underline such that for every s in A, I have an inequality like that. I can write this in a way that is certainly better to understand, easier to understand. I can write it in that way, since this inequality holds component-wise. So for every component, I can take the infimum on the left-hand side over all components. And I see that this is bounded below by the k-infinity function applied to the subprimum. So this inequality basically means that when you range over the whole set A, if you look at all the vectors, then there cannot be too much variation in the components. So actually taking the infimum over all components, we're always bounded below by some function of the subprimum. So that means the points in A, they cannot really approach the boundary of that cone. The only point where they can approach is 0. So that's what the definition actually means. And then we have a theorem which uses this definition, which is the following. First assumption, there exists a subset A of the decay set of gamma, which is weakly star closed, forward invariant, cofinal, and coercive. Second assumption, sigma is globally attractive, and also some mild technical assumption on the underlying graph, but that's not so important. But under these assumptions, we can show that there is a point S0 in the interior of the cone, which admits a complete orbit, such that linear interpolation between the points Sn yields a path of decay. So in that way, we can generalize this method from finite to infinite networks. But we need, in particular, this first assumption. And it's also easy to see that we cannot get around the first assumption, because if we come from the other direction, if we assume that we have a complete orbit, which gives rise to a path of decay, then we can define set A as the union over all the Sns in the orbit and 0, and we see that this set will actually have all the properties that I wrote here. It's weakly star closed, forward invariant, cofinal, and coercive. So this is how you can generalize the method. And then maybe 1 or 2 minutes left. I will skip some things. Just let me show at the end to which kind of gain operators I can apply all these results, so that you don't have the impression, or don't leave with the impression this is just some nice results, but it cannot be applied to anything. So actually, the first class of gain operators where we can get nice and in some sense complete results is max type operators. So those are operators where the monotone aggregation function is for every I the same, and it's the supremum, which is the same as saying that it's the norm on the Banach space L infinity. For this, we can show that actually the existence of the path of strict decay is equivalent to the existence of k infinity function rho, such that the sigma rho system is UGAS. So this is nice because we have a complete characterization of our small gain condition in terms of an asymptotic or a UGAS property of a gain operator. So I'm not going to the proof of that. I'm going to the next class of operators. So this is subadditive and homogeneous gain operators. So gain operators which satisfies an inequality like that, and some equation like this. So if we take like a scalar alpha, we can put it outside, right? Examples are linear gain operators when all the gamma ij's are linear and the monotone aggregation functions are the sums of the components, and also max linear operators where the gamma I are again linear and mu I is the supremum for every I. Then we also have a characterization. The following are equivalent. There exists a path of strict decay, sigma is UGAS, and the infimum over the norms of these vectors is strictly less than 1. This is some kind of spectral radius condition, right? So for proving those two theorems, we can use like the candidate path, so the first construction method that I showed you for the path of strict decay. And finally, we can also apply this stuff to finite dimensional, to the irreducible case, at least when the underlying graph is irreducible. And the nice thing is, like here, we can apply the second method, this linear interpolation method, because we can show that in this case, the whole decay set psi of gamma is coercive. So in this theorem, actually, we can take A to be equal to the whole set of decay, and it will have all these properties, which is very special. I think it will only hold in this particular case. And then we can apply the second method of path construction, the linear interpolation method. And we have a couple of equivalent conditions. One of them is, again, that the sigma rho system is UGAS, but we also have some other nicer condition, like the no joint increase condition, which you might know. Maybe this is the last thing that I'm going to show you, which is this condition. Right, let me stop here, not to go over time too much. Right, I mean, I could also go to the last slide, which is a bit of a summary, but I don't know. Well, maybe I can go through a few of these things here. So what have we done, or what have I shown you? Or what is still open? What are the open questions? Well, first comment here, in the finite dimensional theory, usually a property of those monotone aggregation functions that I did not use is used, namely subadditivity. It's required, but I did not use this property because somehow it seems unnatural to me. For instance, it does not carry over from gamma to gamma rho. So I cannot, if I assume, or if I require subadditivity of the mu i's, I cannot show that gamma rho is a gain operator, which is somewhat not satisfying. So this is why I try to avoid this property. And on the other hand, I don't see actually how it can be used in any meaningful way for the infinite dimensional case. About the next thing, I won't say anything because I didn't show you the slides that you need to understand this. Then the third comment, well, one of the major open problems, right, is to characterize the cofinality of the decay set psi properly. In particular, we do not know if the cofinality of psi, which is needed for the existence of a path of decay, is implied by UGAS of the sigma rho systems, as it is the case in finite dimensions. In finite dimensions, one can use a theorem from topology actually to show that this is true, which is the KKM lemma, but we cannot use it here in this case. And now the last comment, well, we also provided a new explanation why the linear interpolation method, which is used in the finite dimensional irreducible case, why it actually works there. And the reason is exactly the coercivity of the decay set psi, which we cannot expect to hold in any more general setups. In particular, for any type of infinite networks, I cannot see why this decay set should be coercive in the sense of my definition. Right, so we also shed more light on the results that are already known for finite networks, which is nice. So let me end here.